Good afternoon, everyone, and welcome to the final chapter in our series of aquaculture-related webinars designed to bring together science and business to expand and strengthen the United States aquaculture industry. These webinars are a joint effort between the National Aquaculture Association, the North Central Regional Aquaculture Center, and the United States Aquaculture Society. Whether you're currently engaged in aquaculture, looking to get into business, an educator helping others understand aquaculture, or just want to become a better educated consumer, we hope that these webinars will enhance your knowledge and move you forward on your journey to success. Today's webinar is entitled Indoor Shrimp Aquaculture. It will be presented by Dr. Andrew Ray, an assistant professor of aquaculture at Kentucky State University. Andrew has over 10 years of experience in shrimp aquaculture in the southeastern United States, and he will cover the nuts and bolts of indoor shrimp culture and describe some of the logic behind growing shrimp indoors and the opportunities that this technique can create for farmers. Thank you for participating in this webinar series. We hope that you have obtained skills and knowledge that will positively affect the growth of the U.S. aquaculture industry. And with that, I'll turn it over to you, Andrew.
Okay, thank you for that introduction from Alan. I appreciate that, and I'm glad to be with you all today. Thank you for tuning in. As Alan mentioned, and as you know, my topic's on indoor shrimp aquaculture, some of the logic behind that, and some of the ways that you can achieve indoor shrimp aquaculture, grow shrimp indoors, and some of the things that we're doing here at Kentucky State as well. So why would you want to grow shrimp in the United States in general? This is true for other countries as well. I'm most familiar with our specific situation in the U.S., but certainly a lot of this is true in Europe and Asia and many other areas in the world. But in the U.S. specifically, shrimp is the most popular seafood item consumed. The average consumer eats about 4 pounds per person per year. We don't eat a lot of seafood in the U.S., although we should. About 85% of that shrimp, though, is imported from other countries, which leaves us with a big trade deficit. Some questions over food security because we import so much of this particular food item, seafood in general, and some food safety issues at times as well. Some of the imports have been found to contain some compounds that are regulated in the United States and some things that are a little bit questionable. It's also hard to get fresh shrimp in the U.S., even in coastal areas sometimes. With shrimp fisheries, it's often hard to get because of the season or the catch might be down that year. And because of that, there's an inconsistent domestic supply of shrimp, especially fresh shrimp. We can get frozen tails from the supermarket imported pretty regularly, but fresh shrimp is especially hard to get. So why would you want to do this indoors as opposed to outside in ponds where most of the shrimp in the world are grown? Well, if you grow them indoors, you can locate systems like these just about anywhere. If we can create a system that's productive and can be replicated, then we can build buildings, as we know, just about anywhere, and we can replicate that situation. We can situate these near markets, near where people are demanding fresh shrimp, away from the coast, which decreases the cost of the land and potential risk of storm impacts. We can reuse existing infrastructure. Some of the things we're looking at are ag infrastructure and even urban infrastructure or industrial infrastructure that already exists and isn't being used very well right now. The situating these indoors gives us a lot of control over the system as compared to being outside exposed to the environment. And when you have more predictable conditions, you can get more predictable results. And so you're not at the mercy of the weather per se. We can deliver fresh, never frozen, heads-on shrimp close to where the shrimp are grown. And we can grow shrimp large pretty predictably. And that's shrimp is one of the few things that gets a higher price per unit weight the larger it is. which is a nice thing about shrimp. And the heads-on, never frozen is also a real nice thing, because that means no processing is involved with the shrimp, oftentimes. And we can do this practically any time of the year. So how do you grow shrimp indoors? Well, to do this, you really need to use recirculating aquaculture systems, and that term just means, at least in my mind, that means very low rates of water exchange. Specifically, some authors have defined this as less than 1% water exchange per day, although in most cases in the systems I work with, we use much less than that. We're at about 5% of the whole system volume per culture cycle, somewhere around there. To do this, you need to filter solids out of the water and nutrients, especially nitrogen, which comes about as ammonia in the systems. That's what the shrimp excrete, is ammonium. This allows, because we're not exchanging much water, we don't have many inputs, it increases biosecurity quite a bit, significantly increases that. Also, we not only retain water, but we retain heat. So that allows us more flexibility in terms of seasonal operation of these types of systems. And so there's a variety of systems to think about when you want to use recirculating technologies. And three general types. There's a lot of different combinations of filters and various things you can use, but generally people use clear water systems, clear water recirculating aquaculture systems, Biofloc systems, and some hybridization of those two types of systems. And I'm generalizing these a little bit, but generally in clear water systems, your goal is to really take out all the solids, or as many as you can, as much as you can. And so you really lay on with the filtration. You really have a lot of filters to achieve this. Bead filters, foam fractionators, screens, rotating drums, lots of different types of filters you can use to take out solids. Oftentimes you need more than one type of filter to take out different sizes of solids. You need to employ an external biofilter, and this provides lots of surface area for bacteria, for the nitrifying bacteria especially, to colonize. And this is an aerobic container, so it's usually aerated or oxygenated, typically with small plastic beads inside, although anything that provides surface area, the plastic beads are pretty effective at supplying a lot of surface area per unit volume. Sterilization techniques can be thrown on here as well to really try to take out all the potential pathogens in the system. Those techniques include UV and ozone. And then we have Biofloc systems, which are pretty big, pretty different compared to clear water. We actually, in Biofloc systems, allow solids to accumulate. We still have to control the concentration of particulates. Too much is a bad thing. But as you can see in some of these pictures, the solids concentration is quite high, even higher than this at times. And so what happens is these biofloc particles develop naturally. These are dense assemblages of microorganisms, and they're largely held together with through bacterial excretions. It's a natural process. And this is our biofilter and Biofloc systems, all these little particulates and the surface area of the tank and pipes and things like that. And this growth, this natural microbiota here, also provides a food source for animals like shrimp and tilapia. And so the idea here is that you're reducing the amount of filtration, and you're reducing the number of filters on your system, as well as allowing these particles to develop that can then provide some nutrition for the shrimp. So you're recycling some of the nutrients in the system, which is a really interesting concept. So comparing these two, well, on the clear water side, you have more equipment, which means more startup costs, more expense. Probably not much opportunity for supplemental food because you're taking all the particulates out of the water. Probably greater control though, because you have more filtration on the system. Better water quality generally. That's kind of what we're finding in some of our trials where we're comparing these two types of systems here at K-State. reduce risk for disease potential. I have a question mark there because we don't really know the answer to that yet, but it would stand to reason that possibly the potential for bacterial infections at least would be lower in systems with lower amounts of bacteria. Whereas in the biofloc, you have less filtration. You do have that supplemental food. Probably a little less control, though, because you're not doing as much to actively manage the system through filtration. So you have to pay better attention to water quality, and you have to understand what those microbes are really doing in the water column. And then something we've been exploring here quite a bit lately is this idea of a hybrid system. So you've got pros and cons of clear water systems, lots of filters with better control. Biofloc, you have natural productivity but less control. So what we've been working with is trying to capitalize on the benefits of those two systems by making hybrid systems. And so this is not clear water. We don't try to get all the solids out. The systems you see here just have a settling chamber. That's the rectangle or the square tanks over here. Cone bottom rectangular tank that allows particles to settle out on the bottom, and then the water flows over into a drum, 50-gallon drum here, with those plastic biomedia in it. So we're not taking out all the solids, but we have added a biofilter. We are regulating the solids to some extent, and so we find what we're finding is that the water quality, the nitrogen cycling in these systems is pretty consistent because of that biofilter. But there might be the chance for still having that natural productivity in the water as well. So I've used the term biofiltration quite a bit, and this is a very important topic when you're thinking about indoor aquaculture systems. Biofiltration is the way that we deal with ammonia. That ammonia is the metabolite excreted by the animals, and it's very toxic to the animals. So we have to deal with that pretty quickly. And really, in these indoor systems, there's not a lot of algae usually. So we're not looking at algae as a big pathway for nitrogen anymore like you would in a pond. Really, the two primary ways of dealing with this are nitrification, which is an autotrophic process, and assimilation, which is a heterotrophic process. And the exact details aren't, well, they are somewhat important, and it is nice to know them, but we'll talk about it a little more generally than the microbial ecology perspective, I suppose. But both of these processes generally occur in most systems at the same time, and they're bacterial processes. So in nitrification, and this is really what you primarily rely on in external biofilters, you have a situation where the carbon to nitrogen ratio is relatively lower, below about 9.5 to 1, and you get this process going on primarily. This is going to be your dominant process. And that carbon to nitrogen ratio is what's in your feed and then what's in anything else that you add to the system, such as sugar. That's a way of getting more carbon into the system and increasing that ratio if you wanted to. So with a 35% shrimp, 35% protein shrimp diet, which is pretty common, we have a C to N ratio of about 8.5 to 1. So if that's all you're adding to the system, then this is generally going to be your dominant pathway for ammonia. Ammonia is converted to nitrite and then to nitrate. Nitrite's also toxic, but at higher concentrations than ammonia. And then nitrate is relatively not very toxic, although we'll talk about that in more detail in a moment. And this is the graph that you normally see. You see a spike of ammonia, and then that subsides, a spike of nitrite, that subsides, and then your nitrate starts to accumulate, and it will continue on. And then we have assimilation. And so this, you need a higher carbon to nitrogen ratio, above about 12 to 1. And this is a heterotrophic process where the bacteria get their energy from the carbon. And then they need nitrogen to build proteins. And they get that from the ammonia and possibly from other nitrogen compounds as well. And so potentially, some research suggests you could use lower protein feeds to achieve this. But typically what people do in practice is add a carbon source. What I've used in the past is sucrose, which is table sugar, and that works really well. It's a nice pure, well, relatively pure source of carbon, dissolves easily, it's easy to use, easy to get. So a lot of people use this technique at the beginning when they're first starting the system, especially in Biofloc systems, because this process can work pretty quickly as opposed to the nitrification. But you have to be careful, because when you do this, when you add sugar, it increases the biomass. That this picture kind of illustrates that. There's a lot of bacteria that comes about because of this, a lot of solids in the water. And the most important thing is that it decreases the oxygen concentration in the water. It increases the oxygen demand of the water. But if you do this, and if you do this often or on a regular basis, you don't get the accumulation of nitrate, which is one of the big benefits of this. So that's a little bit about some of the underlying principles that dictate these types of systems. And so, you know, I think the next obvious question is, well, what do you do there at Kentucky State? What do you think works pretty well? There's all these different ways of doing it. You can do clear water or biofloc or nitrification or assimilation. But so I'll talk a little bit about what we do here. We've got our Aquaculture Production Technologies Laboratory over here, and then this picture on the right is the Sustainable Aquaculture Development Lab, which we've recently renovated. And mostly a lot of replicated research goes on in here, and then in the Production Technologies Lab we have a commercial scale or near commercial scale system, a couple of systems that I'd like to talk about. Typically we operate a nursery, shrimp nursery. This allows better utilization of space. It allows us to assess the animals before they go into the grow out system, get a count of the animals and estimate their weight, which allows for better feeding practices. The nurseries we use are the same that I just showed you as an example of our hybrid systems, and they work really well. Part of the reason I set these up with biofilters was because we didn't have any marine bacteria or any marine systems in Kentucky when I came here, and so we actually took some seeded biomedia from another system that had koi in it. It was a freshwater system. Put it in these biofilters, adjusted the salinity slowly, and put the shrimp in, and the biofilters worked without a hitch. We cycled through ammonia and nitrite, no problem. So I'm really happy with the way these have performed, and now we just use them routinely. And we normally get about a PL10, post-larvae 10, from a hatchery in Florida. The nursery takes between 30 to 45 days. We shoot for about a 1 gram animal at the end of this. And then we have our production system, which is where the shrimp go after the nursery. We run experiments and things, but we also run shrimp through this as a means of demonstrating some of our research and scaling it up. This is a 20 cubic meter tank. It's about 5,300 gallons or so. And behind the tank, I'll show you a picture in a minute, is a 1 horsepower pump. And we actually use a nozzle-based aeration system, which is similar to a Venturi. Basically, at each one of these pipes that you see here, these smaller pipes coming up, there's 3 of them around the raceway. There's one there and there's one here. There's a nozzle at the bottom of that. Water is pumped through the nozzle. It comes in through the back of the nozzle here and exits through the smaller opening at the front. And then this top orifice is to pull air in, and it's a pretty effective aeration system. It moves water around the raceway, and it also aerates the water pretty well. There's a dividing wall in the center of the raceway. It's a little bit hard to see in this picture, but basically we pump water around that dividing wall, and I think that keeps the water mixed pretty well and keeps the water homogeneous, which is really important because this is a biofloc system, and so we have a lot of particulates in the water. We are using electric heat, but that's not what I'd necessarily recommend. Gas is going to be a little more efficient. It's just what we had available. And we feed this tank, we feed the shrimp in this tank 3 times a day, and then we put about 30% of the daily ration on some belt feeders, some automatic feeders, which you can see here with the green lids. The foam fractionator, this is basically what I've moved to in terms of all or most of my solids management now. This will take out a lot of different sizes of solids, including the dissolved solids. And so we're looking at maybe this is a better filter for long-term water use, possibly. We operate it with a high-pressure pump, which is down here at the bottom of this picture. The water moves in through one of those nozzles at the bottom, and basically you get a lot of really fine bubbles moving up through this chamber, and that causes a lot of foam to accumulate on the surface. The foam builds up in this smaller chamber on top and then overflows, and with it, it brings the solids with it. The solids are attracted to those small bubbles, and they come out with the foam. Really works best in saltwater systems. And then there's a valve here to control the level inside that chamber. These aren't too expensive to make. It's a homemade unit, obviously, made out of PVC. And so pretty happy with that as a solids filter. A more simplistic way of taking out solids is through a settling chamber. This is our design here that we use. It's real simple. It's not my own original design or anything. But basically a large baffle slows the velocity of the water, and as it does, the solids tend to settle out near the bottom, and at the top of the settling chamber, the water is relatively clear, and it travels back to the culture tank. So effective. Used them for a long time. I'm kind of moving towards the Fractionator now. I like it a little bit better in terms of fine tuning. Also, this is a lot of water volume. This is about 250 gallons here. So when you turn it on, you lose an inch or two of water out of your tank, which could be a drawback. And so now I'd like to discuss a specific example that we did here, one of our runs that we've got some pretty good data on, at least. During this particular run, we put shrimp in the nursery the nursery tanks that I described, and brought them up to about 1/2 gram. And then we moved them over to this tank, and they were stocked at 250 shrimp per cubic meter, so that's 5,000 shrimp in this tank. We kept the salinity at 20 parts per thousand. We use an artificial sea salt to do that, and we grew them in the tank for 98 days. And this is a nitrification based Biofloc system, so we're not adding any supplemental sugar to this. The way I did it is and this is important, I get a lot of questions about this. I've got some slides on it too, but we got the nursery really established with the proper bacteria and everything, and then we cycled the water between the nursery and the clean water that we had put into this tank, kept it at a lower volume, but cycled the water between the two, and that really seemed to do a pretty good job at jump-starting the bacterial community in this larger tank as well. And I'll talk a little bit more about starting systems here in a minute. And so our production results out of that tank were that we grew 24 gram shrimp, which is about a 20 count per pound head-on fresh shrimp. And that's a growth rate of about 1.7 grams per week. Feed conversion rate is pretty impressive here, 1.3 to 1. So that means we gave them 1.3 pounds of food for every pound of shrimp that we harvested out of the tank. So very efficient. We had a little problem with shrimp jumping out of the tank during this run. A big problem. About 10% of the shrimp jumped out, actually, even though we had some big barricades to keep them in. So that reduced our survival by, like I say, about 10%. And now we cover the top of the tank real tightly with a plastic mesh to prevent that. But anyway, we produced about 200 pounds of shrimp, and we gave them away to chefs in the area, to chefs in Lexington, Kentucky, and Louisville, Kentucky, two of our major metropolitan areas in the state. And we gave them to some seafood distributors in those two cities as well. And then we took 83 pounds down to our local farmers market here in Frankfort. And this town is about 25,000 people, I believe, is the population or something like that. So it's not a huge town. We've had a lot of fun and a lot of success at farmers markets. This is one where we were out in the cold. It was about 20 degrees this day. But still, lots of people turned out, and we were able to sell a good amount of shrimp and get some good data, too, for our marketing research. So we sold these shrimp for about $12. Well, we sold them for $12 a pound in this particular example. I think we could have gotten more, but we picked $12 a pound. I calculated that our recurring costs of production were about $5.50 a pound. I'm not a economist, but we didn't include the we didn't include the price of the tank, the price of the pump, the upfront permanent costs, and the building as well. The building we're in is a very nice building that you would not want to grow shrimp in on a commercial level. So those are kind of those are some factors that are easily changed by producers. You can get a cheaper tank. You can get a lot of different things. You can dig a hole in the ground and line it if that's available. Certainly the building. In a lot of the farms we're working with, the people already own the building outright. It's been paid for a long time ago, especially with repurposed that infrastructure and things of that nature. So full disclosure, that this $5.50 a pound does not include those permanent costs. It includes things like labor, feed, salt, water, the cost of the post larvae, and things of that nature, electricity as well. We asked the people that we gave these shrimp to rate the shrimp from 1 to 5 on taste, texture, freshness, size, their overall thoughts, and the appearance of the shrimp. And a 1 was the best. And so you can see here that everything scored pretty well. These are the averages, plus or minus standard error. Everything scored pretty well. The one thing that really stands out to me is on freshness, we didn't get anything but 1s, nothing but the very best score on the freshness of the product. And the only way to get fresh marine shrimp in Kentucky, really, on a practical sense, is to do something very similar to what we've done here, to grow them indoors. It's the only way to get fresh shrimp on a regular basis in a place where we have fairly cold winters. So, that really stood out to me in terms of people really appreciating the freshness of the product. And then we asked people what they'd be willing to pay and what the maximum they would pay would be. But this is in dollars per kilogram, by the way. So they were still right around that $12 a pound mark, though. But I think that was probably because we biased them by already having sold them the shrimp for that price. So there's obviously plenty of room to do more research here. But this is pretty encouraging in terms of our marketing results. So like I mentioned, one of the issues that people ask me about a lot is how do I start these systems up? A lot of people have a lot of trouble, especially trying to get that nitrification process established. And the problem with especially with the Biofloc systems, is that there's no substrate. You don't have anything for the bacteria to live on, and they need that, the bacteria do. Basically, a lot of times you start with just clean water, and if you put shrimp in and you raise the temperature and you start feeding them, you're going to have problems. So one of the things you can do is you can add some artificial substrate. This is a tank that we had in South Carolina where we had lots of artificial substrate in the tank. This is some fabric material that was hung in the tank. You can leave that substrate in. The last run of our large raceway, we had some construction netting that we left in, and that seemed to work pretty well. But you got to be careful with that because you can have issues with the water circulation. You can get dead spots underneath that substrate. Harvesting is a real pain if you've got a bunch of substrate in the tank with the shrimp. if you have, or if you can get some substrate of some sort, maybe the little bio wheels that I showed earlier or something else, if you can get some from somebody that you trust, doesn't have any potential pathogens or anything like that, then you're bringing in the bacteria and the substrate with it, and you can jumpstart the system that way in terms of biofloc. Usually in the clear water systems, you can seed your media ahead of time by adding ammonium chloride to the water and trying to get the bacteria jump started that way. When you are starting up your system, you can lower the temperature a little bit. That's one of the nice things about being indoors. You have that control. And so a lot of times if I start to get in trouble with some of this stuff, if I start to get some ammonia or nitrite built up, I'll just lower the temperature a little bit gradually and not too much, a couple degrees, few degrees, depending on the seriousness of the situation. And that can really kind of take the edge off in terms of having a rapid jump in the concentration of some of those compounds. So you have that control, you might as well use it. It'll also slow down the shrimp's metabolism, so you have to feed the shrimp less. There's less nitrogen going into the system and less ammonia coming out of the shrimp. So like I mentioned before, you could also guide the startup with some sugar additions that will take out the ammonia and likewise bring down the nitrite concentration. Be careful with that, though. You can look at some of the equations that are out there in terms of how much to add. Avimilk has a good book that talks a lot about that. But you can also just try a little bit and ramp up a little bit to see the effects. That's kind of the way most people do it in practice. Too much will reduce your dissolved oxygen, so be careful. People ask me a lot about probiotics. I don't know. I don't have one that I just swear by or I use all the time. I've tried them and they've seemed to work at certain times, and then I've tried them at other times and they seem not to work so much. So I think the jury's still maybe out on that, although if you have one that seems to work, use it. I've never heard of anybody using any probiotics and it doing any harm, so it won't hurt. Reuse the biofloc water. If you get a system established, then possibly as little as 10%, certainly 20% of the water, if you reuse that, you'll have that microbial community and your system should behave pretty well. One thing we've been playing around with some is using tilapia to start our shrimp systems. Tilapia are really tough, especially when it comes to ammonia. They can tolerate a lot of ammonia. And they're generally less expensive than shrimp, so you could put them into whatever your system is, feed them, and allow them to help develop that microbial community, that bacterial community. Nile tilapia will tolerate pretty much full-strength seawater if they're acclimated up slowly. But if you're doing a heterotrophic system, you may start with that high carbon to nitrogen ratio by adding sugar at the outset. Another issue, so once you get everything going real well and everything's going fine and you're relying, most people use this nitrification process, and the result of that is nitrate. That's what I use too, and that's a problem for me as well. And once you get up about 400 milligrams per liter of nitrate, it starts to affect the shrimp negatively. Their growth can slow, and it can even kill the shrimp. This is usually 3 or 4 crops for us, somewhere around there. So some of the things we're working with, and still this, I don't have a real great answer for this. Some of the things we're working with is using plants. I know Alan Patillo mentioned Biofloc Systems, I think it is. That's his term. I think he patented that. You could use plants to take up nitrate. Plants will do that. The problem with marine shrimp, anyway, is that there's not a lot of salt-tolerant plants that we know of that are really good at this. This is a picture of some salt marsh grasses. Well, there's not a lot that are really good at this that then could be used for some potentially profitable purpose. These are salt marsh plants from Mississippi, and they will work. They will take up the nitrate given the proper conditions. It's just a question of what do you do with them after that. And we've got some ideas that we're exploring. Some people have used Salicornia, which is, I believe, called sea asparagus, common name, and there's been some success with that as well. People have played around with macroalgae, seaweeds. So there's a lot of research to do in this, and we're doing some of that here actually at K-State. Denitrification is another option, and this is an anaerobic process where you actually allow your filter or whatever it is to be deplete of oxygen, or not completely oxygen free, but almost. And basically it's nitrification in reverse. It takes nitrate and eventually converts it to nitrogen gas, which gases off to the atmosphere. But it is a little bit dangerous to have anaerobic areas directly in your tanks. One of the things I'd like to experiment with more is just taking the water with no animals in it and adding a lot of sugar to it to try to get everything, to try to get that heterotrophic process activated and take up the nitrate. But you'll have to take it, it'll go into the bacterial biomass, and then you'll have to take out those bacteria. You'll have to filter them out. But what you should end up with, and again, this is research, but what you should end up with is water that doesn't have any nitrate in it, or very little. So still an issue, something that we're working on. So if you want to learn more about indoor shrimp aquaculture, I would encourage you, if you can, come visit us here at Kentucky State University. We're always open for tours. We're a publicly funded institution, and we are here to help you and to share the knowledge that we have about this. We have some systems set up that you can come and look at and kick the tires a little bit. There's a link to a YouTube video here if you haven't seen it. This QR code also takes you to it. KSU Aquaculture has a Facebook page, and we post a lot of things like workshops and this webinar, for instance. And so be our friend on Facebook and stay updated on things like that. We have a website as well. If you don't do Facebook like me, you can go to the website, and we try to keep that updated as well with new information. And here's my email address. Feel free to contact me as well. And so thank you very much for tuning in again. Really appreciate the opportunity to be here with you all today.